Take a look at this handwritten digit. It's clearly a 7 to us. Our brains effortlessly recognize it, even with its unique quirks and imperfections. But what does it actually mean for a computer to recognize this handwritten digit? How does it go from a jumble of pixels to the confident declaration, "That's a 7"? This isn't just a theoretical question. It's the foundational challenge behind everything from reading zip codes to unlocking your phone with facial recognition. It's about teaching machines to perceive the world, and it's the core of what we'll explore in this deep dive. Welcome to Build Weekend Projects, where we don't just show you what to build, but why and how it works at a fundamental level. In this series, we believe that true understanding unlocks limitless creativity. And today, we're diving into the very first principles of how a computer can learn to see. To understand how a computer recognizes our 7, we first need to understand how a computer sees anything at all. For a computer, an image isn't a picture, it's just a grid of numbers. Each tiny square in this grid is A and LT, yellow and GT, pixel and LT/yellow and GT. And each pixel, for a simple black and white image, can be represented by a number between 0 and 1. 0 for pure black, 1 for pure white, and shades of gray in between. So, our handwritten 7, which might be a 28 by 28 pixel image, becomes a long list of 784 numbers. Each number tells the computer how dark or light that specific spot is. This list of numbers is R and LT, blue and GT, input and LT/blue and GT. Now, how do we get from this list of numbers to the idea of it's a 7? We need a way to combine these numbers, to give some pixels more importance than others. Think about what makes a 7 unique. It has a strong horizontal line at the top, and a distinct diagonal line. We can assign A and LT, green and GT, weight and LT/green and GT, to each pixel. A high positive weight for pixels that, when dark, strongly suggest a 7. A high negative weight for pixels that, when dark, strongly suggest it's not a 7. And weights near 0 for pixels that don't tell us much either way. To combine these, we simply multiply each input pixel's value by its corresponding weight. If a pixel is dark, high value, and has a high positive weight, it contributes a large positive number to our "is it a 7" score. If it's dark but has a high negative weight, it contributes a large negative number. Then, we sum up all these products. This gives us a single number, a raw score. A very high positive score means yes, very likely a 7. A very low negative score means no, definitely not a 7. But this raw score isn't quite enough. What if our 7 is a bit faint, or drawn very small? The raw score might be lower, even if it's clearly a 7. We need a way to adjust our threshold for what counts as a 7. This is where the and LT, yellow and GT, bias and LT/yellow and GT, term comes in. We simply add this bias to our raw score. A positive bias makes it easier to reach a yes decision, shifting the threshold down. A negative bias makes it harder, shifting the threshold up. It's like setting the difficulty level for recognition. Finally, we need to make a clear decision: is it a 7 or not? We pass this adjusted score through an and LT, yellow and GT, activation function and LT/yellow and GT. For now, let's imagine a simple one: if the score is above 0, it's a 7. Otherwise, it's not. This entire process, taking weighted inputs, adding a bias, and passing it through an activation function, is what we call A and LT, yellow and GT, neuron and LT/yellow and GT. It's the fundamental building block of a neural network. And LT, break time equals 2000 ms/NGT, but a single neuron, while powerful for simple decisions, isn't enough to recognize complex patterns like our 7 reliably. What if we have to distinguish a 7 from a 1? Both have diagonal lines. A single neuron might get confused. This is why we don't just have one neuron. We have NLT, yellow and GT, layers NLT/yellow and GT, of neurons. Imagine a layer of neurons whose job it is to detect simple features. One neuron looks for horizontal lines, another for vertical lines, another for diagonal lines. Our input image, the grid of pixels, feeds into all these feature-detecting neurons simultaneously. Each neuron calculates its own score based on its specific set of weights. The outputs of these neurons then become the inputs for the next layer of neurons. This next layer can combine the simple features from the first layer to detect more complex patterns. For example, one neuron might combine a horizontal line and a diagonal line to recognize the top part of a 7. This hierarchical structure, where simple features combine into more complex ones, is incredibly powerful. It allows the network to build up a rich understanding of the input image, much like our own brains process visual information. Finally, the last layer of neurons, the NLT, yellow and GT, output layer NLT/yellow and GT, makes the final decision. For our digit recognition task, we might have 10 neurons in this layer, one for each digit from 0 to 9. The neuron in the output layer that activates the strongest, or produces the highest score, is the network's prediction. If the 7 neuron has the highest output, the network confidently says, it's a 7. NLT, break time equals 2000 ms/NGT. Imagine trying to do this by hand. For each of the 784 pixels, you'd have to decide how important it is for a 7, then for an 8, then for a 9, and so on. Then you'd have to combine those decisions, and combine those decisions. It would be an impossible task. But with a neural network, we've built a system where simple, repeatable operations, weighted sums, biases, and activation functions combine across layers to perform incredibly complex pattern recognition. That intelligence emerges from these simple interactions. So, when a computer recognizes our handwritten 7, it's not magic. It's the result of millions of tiny calculations, where each pixel's value is weighted, summed, biased, and activated, layer by layer, until a final prediction is made. Here's what we've learned today. First, images are just grids of numbers, and these numbers are our NLT, blue and GT, input NLT/blue and GT, to the network. Second, the fundamental building block is the NLT, yellow and GT, neuron NLT/yellow and GT, which takes weighted inputs, adds a NLT, yellow and GT, bias NLT/yellow and GT, and makes a decision using an NLT, yellow and GT, activation